All right, in the last part of today's lecture, we're going to put to use some of the things we learned in parts 1 and 2 and actually talk about how we can use RNNs to build practical models for solving practical problems. The first thing that we're going to talk about, which is actually pretty important, is autoregressive models and structured prediction. So I mentioned briefly at the end of the previous part that most RNNs that we actually use in practice have multiple inputs and multiple outputs. And that might seem a bit perplexing at first because many of the problems that we want to solve actually have either a single input and multiple outputs or a single output and multiple inputs. So why is it that we usually use RNNs with multiple outputs and multiple inputs? Well, it's because most problems that require multiple outputs have strong dependencies between these outputs. That might seem like a slightly cryptic statement, so let's try to make it a little bit more intuitive. These kinds of problems are sometimes referred to as structured prediction. They're referred to as structured prediction because the thing that you are predicting, the output sequence, has structure. In contrast to something like a label has no structure. A label is just a value of a single discrete variable. If you're outputting something like text, text has internal structure. Basically, separately from whether the output of text is the right answer or not, there are relationships between words and text that determine whether it's valid text. So basically, if I ask you some question, if I ask you, for example, what did you do over the weekend? And you could tell me, you could tell me some sentence, you could tell me, I flew a spaceship to the moon. Now that is not the right answer, that is not true, it's false, but it's a valid English sentence. You could instead say, I gibberish, purple, xylophone, right? Like, that's neither true nor a valid sentence. So we want outputs that are true, but we also want outputs that are valid, that obey the internal structure. And that's why we call it structured prediction. Okay, so a classic example of this is text generation. Let's say that you have a training set that consists of 3 sentences. I think, therefore I am, I like machine learning, and I am not just a neural network. And let's say for now that you don't care about generalization, you just want your model to basically memorize these 3 sentences. Okay. So we'll treat words as categorical variables. So every time step will be a different word, and it'll just be one of n possible words. So your neural network will read as input. Maybe we'll prompt it. We'll prompt it with the first word in the sentence. So we give it the input I, and then we ask it to complete the sentence, and it can complete it in 3 different ways. So maybe it's a really good network. At the first time step, it knows that there are basically 3 words that could follow the word I, and they're all about equally likely. Think, like, and am. So these are the second word in each of these sentences. And then we have a softmax distribution over these. So the softmax turns these into probabilities, and we have a probability of 0.3 for think, 0.3 for like, and 0.4 for am. And then we'll sample randomly from this softmax distribution to actually pick the second word. So maybe we randomly pick the word think. So now the network is completing the sentence as I think. And then we proceed to the next time step. So we compute the, we have this linear layer that uses the previous activations to compute the new activations. And then we have our output at the second time step, and that again goes through a softmax distribution. The trouble is that the network doesn't know which word was randomly sampled from that softmax. So the network thought it produced an output that is 30% think, 30% like, and 40% am. Without knowing what you sampled, at the next time step, it's going to still be in this kind of superposition of possible sentences. So it's going to say, well, I told you what is the distribution of second words in the sentence. Now you're asking me what is the distribution of third words in the sentence. Well, the third word is equally likely, therefore, machine and not. Right? Because those are the third words in these sentences. So the network is doing exactly what you asked it to do. The problem is that you're trying to sample these words independently. So in the second time step, you're going to randomly sample, and maybe you randomly get machine. And then at the third time step, same thing. It gives you a distribution over fourth words in the sentence. And you might sample just. So now your network is doing everything correctly. Your network actually learned the distribution over these 3 sentences, but the completion you got is, I think machine just. So your generation makes no sense, even though the network actually did a great job of learning this distribution. So we get a nonsense output, even though the network had exactly the right probabilities at every point in time. And that's because in this task, the covariances between the words matter just as much as the probabilities of getting the correct words. Okay, so here's what we can do to fix this. And this is why it's so important to have networks that take in variable length inputs and variable length outputs. What we're going to do when we actually run this network to complete a sentence is we're going to sample from the softmax at the first time step, and then we will feed our sample as an input at the second time step. And this will basically tell the network what it is that we sampled. So now the network knows that it's not just predicting the third word in any sentence, it's predicting the third word in a sentence where the first words are, I think. And now it's going to correctly predict that if the first two words are, I think, the third word is probably going to be, therefore. And it will sample that word, feed that in as input, and then complete the fourth word, which most likely is I. So then it will correctly generate, I think, therefore I am. If on the first time step it randomly samples like, then on the second time step, it'll assign a much higher probability to machine. Okay. So the key idea is that past outputs should influence future outputs. And the way that you get past outputs to influence future outputs is by treating yesterday's output as today's input. Okay, and this basic design is used for virtually all RNNs that have to output a structured sequence. Things like image captioning models, video prediction models, they will all use models of this sort. So basically, you very rarely have multiple outputs without multiple inputs because you want past outputs to influence future outputs. Okay, now how do we train this thing? Well, the simplest way to train it, which is the most obvious, is to just set the inputs to be the entire training sequence and the ground truth outputs to be the same sequence but offset by one step. So basically, instead of asking the neural network during training to just dream up a sentence, you're really asking it to complete a sentence. You're saying, at time step t, take all the words from time step 1 to t and output the word at time step t plus 1. So your x's are going to be the all of the tokens in the sentence, except for the very last one. I think, therefore, I am. All the tokens in the sentence. And your ground truth outputs are going to be all the tokens shifted back by 1, and then the last one will be replaced with a stop token. So basically, this network is being taught that if it sees I, it should output think. If it sees I think, it should output therefore. If it sees I think, therefore I am, it should output a stop token indicating the sentence is done. And that way at test time, when you use this to predict a sentence, then you eventually get a stop token, and then you know the network is finished with that sentence. So this teaches the network, to, for example, to output the word am if it sees I think, therefore I. All right, so that's the basic design for an autoregressive model. There's a little bit of an issue with this. The basic design I had on the previous slide, if you use it to train a network, there's a good chance it'll work pretty well. But if you use it to train really complex networks for very long sequences, you might start seeing some problems. And the problems that you might start seeing are due to something called distributional shift. So here's the trouble. Let's say that you have the same example as before, but the network is making some small mistakes. So maybe for the first token, it assigns a 60% probability to think, a 30% probability to like, and a 10% probability to some random word. Let's say the word is drive. Why is it doing that? Well, maybe it just didn't train very well, maybe it makes some mistakes. All models make some mistake with some small probability. Usually you wouldn't worry about this, because the most likely token is actually a very reasonable one. But let's say that you're decoding, and you got unlucky and you sampled this 10% thing, the word drive. In practice, what might actually happen is you might get some input that is similar to one you've seen before, but not exactly the same. But in this case, in this example, you just have a low probability output. That's also a potential problem. And now you're going to use this as the input at the next time step. And the problem that happens in this case is that the network has never seen this token used as an input before. It's just some random token. It doesn't really belong in this sentence. Now, you made a small mistake on that first time step. You can still recover. You can still turn this into some reasonable sentence. The trouble is that because you're now feeding a token into this network that is so different than what it ever saw as the completion for the sentence, maybe it saw this token in other contexts, but it never saw it in this context, it's just going to be completely confused. So at the second time step, what it will output is just some completely crazy thing. Some complete nonsense, and when it samples from that complete nonsense, it basically it's done for. It's not going to produce anything reasonable. So it's going to produce complete nonsense because it never saw inputs like this before, it doesn't know what to do with them, and it doesn't produce reasonable results. The problem underlying this is a discrepancy between training and test. Because during training, the network always saw true sequences as inputs, but at test time, it's suddenly getting its own inputs, which are potentially incorrect. So the problem is not that it made a small mistake at the beginning. The problem is that that small mistake compounds by then becoming an erroneous input into the model. If we weren't giving it this input, it might actually still recover. It might still produce a sentence that's not perfect. It might say, I drive, therefore I am. But it would at least be a sane sentence. Like most of the sentence would be reasonable. But as soon as it gets this crazy input, it'll now produce complete garbage because it's just not used to seeing such crazy inputs. This is called distributional shift because the input distribution shifts from true strings during training to synthetic strings at test time. Essentially, true strings have a different distribution than fake strings, and the network was trained to take true strings as input, and now it's being tested on fake strings, which it's not used to, and therefore doesn't deal with correctly. And this is a big problem because even one random mistake at even one time step can completely scramble the entire output. So one solution that has been proposed to deal with this is actually inspired by an old trick in reinforcement learning adapted to training RNNs. And the method, at least in RNN world, is called scheduled sampling. In reinforcement learning, it goes by some other names. And we'll actually learn about that when we talk about imitation learning later. So here's the diagram from the scheduled sampling paper that illustrates the basic idea. During training, usually we want to feed in the true string as inputs. But what we're going to do with scheduled sampling is we're going to make a random decision at every step in time. With some probability, we will give the network the true input at that time step. And with 1 minus that probability, we'll actually give it its previous output as an input. Now, crucially, we don't differentiate through this edge, so the network doesn't know that it's getting its own output as an input. And that's very important because differentiating through random sampling is very, very hard. So you can basically think of this as randomly replacing the true input with the network's own output at the previous time step with some probability. And this really helps because now, during training, the network sees its own outputs as inputs, and therefore when it sees that at test time, it's not completely confused. Now, it still doesn't know how to change the sentence. So basically, this would teach it to say, I drive, therefore I am. Now, is I drive, therefore I am a reasonable sentence? Well, probably not, and if it's trained really well, it'll eventually stop saying drive and start saying think, but it will still help it to patch a lot of those mistakes. It'll basically have it recover. It won't recover in very graceful ways, but it's better than failing completely. So now here's a thought exercise. How do we want to choose this probability for replacing the true input with the model's own previous output? So if we always replace the true input with the model's previous output, the model might be really hard to train because early on the model produces most of the garbage. So then it's going to get a true word as input on the first time step and then a bunch of garbage at future time steps, and it will probably just learn to ignore the input and just generate arbitrary words. So that's not good, that's not what we want. Intuitively what we want is we want at the beginning to mostly feed in the true inputs. And then once the network gets pretty good so that its outputs actually make sense, towards the end we want to mostly feed the model's own predictions to mitigate this distributional shift. So what the authors of this paper recommend, and that's why they call it scheduled sampling, is to put a schedule on this probability, where the probability of using the true input starts off really high and then gradually drops. And since the probability of using the model's output is 1 minus that, that means that over time you're gradually using the true inputs less and the model's outputs more. And they propose a number of different schedules that you could experiment with, like a linear schedule or an exponential schedule, but they all have the same flavor, that the probability of using the true input starts off high and then goes down to 0 towards the end of training, where at the end of training you're mostly training the network on its own previous outputs. Except of course for the very first input, which always comes from the data. All right, so that was a brief aside, and in practice, you don't have to use scheduled sampling, especially for shorter sequences or for easier models. You can often get away with regular training, but scheduled sampling can really help with more complex models. All right, now we can use RNNs in a huge number of ways. One of the big advantages of RNNs is that they afford a great deal of flexibility. So with regular feed-forward networks, you basically have kind of one-to-one mappings, so one input, one output. With RNNs, you can have one input to many outputs, many inputs to one output, many inputs to many outputs, where you first read in all the inputs and then produce all the outputs, and so on. So this first one to many, that's maybe a good fit for something like image captioning, where the input is an image and the output is a sequence of text. Many to one could be a good fit for something like activity recognition, where the inputs are frames in a video and the output is the label classifying that activity, playing basketball or car racing. Many to many, where you first read in all the inputs and then produce all the outputs, that could be a good design for something like machine translation, because you might want to read in the entire string in English before producing the entire string in French. You don't want to translate English to French word for word. You want to actually read in the whole sentence and then translate its meaning. And this kind of many-to-many design, I apologize, the text is a little cut off, that could be a good design for something like maybe frame-level annotation. So the inputs are individual frames in a video, and you want to annotate every frame with what's going on in that frame. Now, as I mentioned before, in practice, if you have many outputs, you're actually going to have many inputs. So in actuality, the one-to-many and the many-to-many probably would be implemented like this, because you want to have this autoregressive process for producing those outputs. And that's actually what we see in reality. All right, now let's briefly talk about a few implementation details. One of the things that we often do with RNNs is that we have an RNN backbone in our model, come somewhere in the middle, and then we use a non-recurrent encoder. This is especially common if you have image inputs like videos. So you might have just a regular convolutional network, which then feeds into the RNN. So the convolutional encoder is placed before the RNN layers. This is very common to do with image inputs. Now you could also have some kind of complicated decoder. So you could take the output of your RNN or LSTM cell and feed that into multiple layers, maybe multiple fully connected layers, before producing the output. And that's also sometimes done. It's a bit less common, since you could just use more RNN layers. So the feed-forward encoder, using something like convolutional layers, is pretty common, especially for images. The multi-layer decoder is sometimes used, but it's a bit less common. Now, you could also have multiple RNN layers, and that's totally reasonable. So basically, you can have the output of your RNN layer at a particular time step feed into another RNN layer, and then eventually into a softmax. So it's easy to stack as many RNN layers as necessary. And you could even implement recurrent or LSTM convolutional layers. So if you really want your network to be fully recurrent at every single layer, you can actually do that. And you can actually make your convolutions recurrent too. It's a little bit expensive computationally, but conceptually it's very simple. Basically, you have this operation for the LSTM. This is the only operation that uses learned parameters in the LSTM. And you just replace this with a convolution. So as I had it on the slide, it was a matrix multiply, but you would instead do a convolution, which basically means that every filter becomes a little LSTM cell. So every filter takes in its current receptive field as input and the previous HT-1. And you can just think of those getting concatenated. Now, another trick that you can use with RNNs is something called bidirectional models. Let's use an example like speech recognition. So in speech recognition, your inputs are sequences of sounds, and you want to produce maybe the corresponding words. Now, mostly the word at a particular time step will depend on the sound at that time step, but not exactly, because sometimes the rest of the sound will influence what word you think it is. Because speech just kind of tends to be slurred together, and it's not just like cleanly aligned in time. So the problem is that the word at a particular time step might be hard to guess without looking at the whole utterance. So you really want the sounds at future time steps to inform your guess about the word at the current time step. For example, you might not be able to tell whether a word is finished until you hear the ending of the phrase. And this is an even bigger problem in things like machine translation. Now there we might use slightly different types of models, but these kind of bidirectional models could work too. Right, because in machine translation, you don't want to translate word for word. You want to actually see the whole utterance and then translate it. So a bidirectional model is basically an RNN where you first have a layer of recurrent connections running forward, and then you have another layer above it running backward. And that means that at each time step, you have information from both the past and the future. And then you have a softmax layer that outputs the answer. So the way that you perform a forward pass in this bidirectional RNN actually looks like this. So before you can produce the output at time step 2, you have to run the bottom RNN through steps 3, 4, and 5, so that you can start running the backward RNN through steps 5, 4, 3, and 2, and now you have everything needed to process the answer at that time step. So implementation-wise, this is really simple. The outputs, the y-hats from the bottom RNN, serve as inputs into the top RNN. And backpropagation works exactly the same way using this reverse mode automatic differentiation that I described in part 2. So implementation-wise, it's actually very simple to implement. Conceptually, it maybe takes a moment to wrap your head around what exactly this thing is doing, but what it's really doing is it's allowing you to integrate information from both the past and the future when you want to make a decision at a particular time step. So this is actually a significantly more powerful model, especially in settings where you want information from the future to make a more informed decision in the present. All right, so that's kind of the technical portion of the lecture. Now I want to go through a few examples, somewhat vivid examples of RNNs doing cool stuff in practice. So these are some examples from Andrej Karpathy, who used LSTMs to learn generation for a variety of different data types. So here he trained an RNN on the collected works of Shakespeare. So he just took a bunch of Shakespeare texts, sonnets, plays, etc., used them to train RNN. This is actually, I think, coming from some other literature, but a similar principle. Here he's showing the output of the model at different stages in training. So early on in training, it just kind of produces garbage characters. Later on, it starts producing things that look a little more like words. Then it starts, mostly saying reasonable words with a few spelling mistakes, and then eventually it even gets entire phrases and even sentences that look reasonable. And then he used this to generate kind of fake Shakespeare, essentially. If you look really closely, you can tell that this is obviously not a real play. It does put in names of characters, but the names are not entirely reasonable. So you have a second senator, maybe that learned something from like Julius Caesar. And then you have like Duke Vincentio. Now probably second senator would not be talking to Duke Vincentio. That doesn't really make sense, different time period. But at a high level, it's kind of sensible play-like looking text. Now this was a few years back. This was around 2016. Andrej also did some, more silly experiments where he downloaded LaTeX source code for a algebraic geometry textbook, and he had his RNN basically generate fake LaTeX, and that fake LaTeX could actually be compiled into a real PDF with like fake theorems and fake lemmas and stuff and so on. Now, if you actually look closely at some of these lemmas and some of these proofs, they make no sense. Like, for example, lemma 0.3 says, in situation question mark, hence we may assume q prime equals 0. That's not a valid lemma statement. But at a high level, it actually looks kind of like sensible LaTeX. These days, these kinds of generation models have gotten a lot more sophisticated. So these are some examples from a model called GPT-2. This is not actually an RNN. It's actually a different type of model called a transformer that was invented at Google. But here it's being used in a similar way. And there's an input prompt. And this text written by a person that was provided to the model. It says, in shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. Now, this was text that a human being wrote, and then the model is told, look at this text and then complete it. Basically, generate more text that is plausible as text that follows this prompt. And the rest is generated by the model, and it says the scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. Jorge Perez, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when they found a small valley without no other animals or humans, etc. So you can see that the model is actually doing some pretty sensible things in terms of grammar and structure. But perhaps even more surprising, it's actually getting some semantic details, some very subtle details right. Like, for example, the biologist has a name that is plausible for the name of a scientist from the University of La Paz who would be working in the Andes Mountains. Right, so it didn't generate like some, a name that sounds South Asian or East Asian or European, Western European, like, or Anglo-Saxon. Generated a name that sounds like a plausible name for somebody, at University of La Paz. So even subtle details like that are actually captured. So we'll talk about these types of models more in a later lecture when we talk about NLP. All right, so to briefly summarize the main points. Recurrent neural networks, these are neural networks that can process variable length inputs and outputs. And you could think of them as networks with an input and output at each layer. You can think of them as basically variable depth networks, or equivalently, you can think of them as networks that have a notion of time. Training RNNs is very hard. You have vanishing and exploding gradients, but you can use special types of RNN designs like LSTMs and GRUs to address these issues to some extent. Generally, though, you still need to spend a lot of time tuning hyperparameters and getting things right for them to train well. In practice, we almost always have both inputs and outputs at each step. And this is because we usually want structured prediction. So if you want variable length outputs, you want to feed the previous outputs as inputs to allow the network to capture temporal dependencies. And then you can use scheduled sampling to handle the resulting distributional shift. There are many variants of RNNs for various purposes, sequence-to-sequence models, bidirectional models, and so on. And you can even RNNify a convolutional layer if you wanted to. So RNNs are a very flexible basic design. And this is the basic foundation that we'll build on when we talk about all sorts of applications of sequence models in later lectures.